Hello, precalculus class. So today you're going to learn about what a matrix is and how we can use it to solve various problems. So all it is an array of numbers in a rectangle, and you have rows. So those are going across, and it can be an unlimited number of rows. So they count them 1, 2, blah, 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 all the way to row M, as in that would be your maximum number of rows. And then you can have a bunch of columns going across. Those go up and down, and they all the way, it can be unlimited size number of columns to column N. So every element in an array has two subnumbers. The first one, I, index I, is the row index. So which row is it? Is it row 1, row 2, row I, row M? Or the column index is the second number, and that is, this is column 1, this is column J, this is column 4, column 2, column N. So we talk about the size of a matrix, and that will be M by N size. So we always talk about rows by columns. And I'll just kind of draw in a little example here. Let's say I have this matrix here, 3, -2, 4, 0. Do you notice that we only have one row, but we have 4 columns? So if I asked you for the size of this matrix, we'll call it matrix A. The size of the matrix is 1 by 4. It's always row by column. And matrices can be any size. All right, and then we can also refer to this as element A11, A12, A13, A14. So the first number is the row number, and the second number is the column number. This is just an example of how you might arrange some data in a matrix. So we are given some information here. We have 900 people, and we know how it breaks up male versus female. And then within the male category, we have whether they thought defense spending was too high, too low, or no opinion. And likewise in the female category. So this is really data that's kind of what we call a two-way table. And we've got male and female as your rows, and then the too high, too low, and no opinion as columns. So if we wanted to just look at the data in the matrix, now that we've set it up, we're just looking right here. So this is a 2-row by 3-column matrix. And just an example of what you might do once you know the reasons for the data, and then you can just look at the numbers. One thing we'll need to be able to do with matrices is to add and subtract matrices, scalar multiply them, and then multiply two matrices together. Some requirements. If you're going to add or subtract matrices, then they must be the exact same size. They must be identical row and column sizes. Matrices must also have the same number of columns in the first matrix as rows in the second matrix in order to multiply. So that's a little bit confusing, and that is something we'll go through more. But if I wanted to multiply B times C, I have to double check that B has the same number of columns, 3, as C has rows. And as long as that is the case, we are able to multiply those two matrices together. Likewise, we're able to subtract A minus B because we're both, let's see, the size, let's just go through all the sizes. The size of A is 2 by 3, row by column. The size of B is 2 by 3, 2 rows, 3 columns. So we can subtract A minus B. We could add A plus B. And then C is 3 rows by 1 column. So we can't add C to A or B. You can always scalar multiply. That's just distributing in a -2. We're actually going to go through this exercise with these same matrices in a minute. So here's some notes about addition and subtraction of matrices. It says, first of all, two matrices are equal if that they have the same number of rows and columns, and every entry matching corresponding entry in A is equal to the entry in B. So that's just kind of when are two matrices equal, and that's when everything about them is equal. They are the same size and every entry is the same. Then if A and B are both m by n matrices, then the sum can be found and you just add up all corresponding entries. So the result of A plus B will also be an m by n matrix. So if you've got a 2 by 3 and you're adding it to a 2 by 3, you'll end up with a 2 by 3. Likewise, the same for a subtraction of matrices. They must be the same size, and then the result is the same size. And we have a couple properties, the first of which is commutative property is true, and we can look at this. Doesn't matter which order we add matrices in. Likewise, the associative property of matrix addition holds true. So it doesn't matter which two you add first, and then when you add in the third, you're going to get equal results. And here's some notes about scalar multiplication of matrices. So if you have an m by n matrix A, and S is a scalar, so a scalar is just a number, integer, fraction, doesn't matter, but it's not a matrix, then we can multiply every element in the matrix by the scalar, and that's called scalar multiplication. Some properties, and this is just kind of the order in which you do stuff. You can, if you have two scalars, you can multiply the two scalars together first, then distribute them into the matrix A, or you can distribute one into the matrix A and then the other, and you'll get the same results. Likewise, you can add the two scalars and then distribute them to the matrix, or you could multiply the matrices by them separate and then add them together. Likewise, if you had two matrices, you could scalar multiply them both. You could kind of say this is the distributive property of scalar multiplication. All right, let's do some examples of matrix subtraction and scalar multiplication. So we're just going to do these two, and we're going to hold off on these two. So if we want to do matrix A minus B, and each matrix A and B, they're both 2 by 3s. Always double check that. So my result is going to be 2 by 3, and I kind of give myself the framework, and we're just going to do A minus B. So 1 minus negative 2 is a 3. Negative 3 minus 0 is negative 3. Negative 2 minus negative 5 is a positive 3. 0 minus negative 1 is 1. 4 minus 4 is 0. 8 minus 3 is 5. And that's your result. And then if we're going to do our scalar multiplication, I look at that as just like distribution. So I'm multiplying negative 2 times the B matrix, which is 2 by 3 still. So my result will also be a 2 by 3, and I'll just distribute that in. So you end up with 4, 0, 10, 2, negative 8, negative 6. And there you have it. We will come back to this slide to do those other two examples in a few minutes. All right, now we're going to talk about matrix multiplication. This is probably the trickiest part. The key is when you look at the size of matrix A that you're multiplying by matrix B, I always do this first when I'm asked to multiply two matrices together. You want to make sure you have a match in the inner column and row. So this is the column of the first matrix, and the number of columns must match the number of rows in the second matrix. As long as that is the case, then you can multiply them together. And the result will be the outer values, or an m by n matrix in this case. The easiest way to see this is with an example. So we're going to look at this first one, which is matrix R times matrix C. First, let's check their sizes. So matrix R is 1 row by 3 columns. And matrix C is 3 rows, 1, 2, 3, 3 rows times 1 column. And look at that, we have that inner match. And it also tells me what the result is going to be. And that is going to be a 1 by 1 matrix. I'm making this a little bigger because you see what we have to do. So in order to do this multiplication, what you're going to do is take each row value times each column value and then add them together for that one cell. So I'm going to take row 1 times column 1. So 1 times 2 is 2. And I'm going to add that to the next value in row 1, which is negative 2, times the next value in column 1, which is 2. Negative 2 times negative 1 is 2. And then the next value in row 1 is 4 times the last value in column 1, which is 3. So you have plus 12. Add those values together and you end up with 16. And that is your result of the matrix multiplication. Another example will be helpful. So now we're going to look at A times B. And let's just check the sizes. A is 2 rows times 3 columns. B is 3 rows times 2 columns. So we have an inner match of the 3 and the 3. And our outer dimensions are going to be our result. So our result is going to be 2 by 2. I'm making this much larger because we have lots of pieces to put together. So for my first row and my first column, I look at my first row and my first column. And in order, I'm going to multiply the pieces and adding. So 3 times 2 is a 6, plus negative 2 times negative 1, so that's plus 2. And 1 times negative 3 is a minus 3. I'll go and add those together later. Now I'm going to look at row 1 with column 2. So row 1 with column 2. And that will go into the cell referenced 1, 2. All right, so 3 times 4 is a 12. Negative 2 times 3 is a minus 6. And 1 times 1 is a 1. All right, next one is going to be row 2 times column 1. All right, so 0 times 2 is 0. 4 times negative 1 is a minus 4. And negative 1 times negative 3 is a plus 3. So the key thing to remind yourself or keep repeating is row times column. Across times up, down. All right, our last cell here is row 2, column 2. Row 2, column 2. So 0 times 4 is 0. 4 times 3 is 12. And negative 1 times 1 is minus 1. So we can put this all together, just simplify each cell into one result. And A times B is going to be, let's see, we have a 5 and a 7 and a negative 1 and an 11. And that's your result. So first of all, it changes the dimensions from 2 by 3 and 3 by 2 to a 2 by 2. And it kind of is a number of little multiplications together. So you might ask yourselves why later that we do this, and I will show you an example, but it's really a lot of times you can use weighted averages by doing this, or kind of combining a whole lot of data into one result. Okay, so this is AB, A times B. The question is B times A the same result? So let's check that out. All right, I'm going to move this up. And the first thing we have to think about when we do B times A is the dimensions. So B, once again, is a 3-row times 2 columns. And A is here, and that is a 2 row times 3 columns. So yes, we've got that inner match, and my result will be the outer. So this is going to be a much larger matrix when we're done. This is going to be a 3 by 3. So let's do this. So we're going to start. What's hard here is I'm kind of looking at them backwards. I'm not going to rewrite them. But we're going to start with this row here times this column here. So 2 times 3 is a 6, and 4 times a 0 is a 0. Then we'll just go across here. So we're going to take that same row, 2 and 4, and do it on each column. So 2 times the next column is -4, and then 4 times 4 is 16. And then lastly, this row times the final column, 2 times 1 is 2, 4 times -1 is -4. And we'll add them together in a minute. All right, so we'll go to another color, and we're now working on the second row times the first column again. -1 times 3 is a -3. So remember, this is second row and first column. So we have -1 times 3 is -3, and then 3 times 0 is 0. And then we have -1 times -2 is 2, 3 times 4 is 12, and -1 times 1 is -1, 3 times -1 is -3. And we're on to our last row right here, last row, row 3 times first column. -3 times 3 is -9, and 1 times 0 is 0. -3 times -2 is a 6, and 1 times 4 is a 4. And lastly, -3 times 1 is -3, and 1 times -1 is -1. So we are just about done. We just need to simplify this a bit. And let's add them all together. So BA, or B times A, is this resulting 3 by 3 matrix. 6, 12, -2, -3, 14, -4, -9, 10, -4. And that is matrix multiplication. One thing we'd like to check is matrix multiplication commutative? And I'm going to tell you right now, the answer is no. It is not commutative, in that you can't switch the order and get the same result. So like we did in the last problem, we did A times B, and then we did B times C. They weren't even the same size. In this case, they are going to be the same size, and you can go through it. You can start with doing A times B. So remember, rows times columns. And when you do that, you're going to end up with, so I'll have you pause it and try it on your own, 7, -17, 12, and -28. And then you can switch the order and do B times A. So in this case, you'd be doing the B column times the A row first. And this result will be different. And you end up with -2, -6, -5, and -19. So you can go ahead and try that on your own. Okay, so let's look also at some other properties that do apply. One is the associative property. Note in this one, you're not changing the order. You're just, so it still goes A, then B, then C, but you're doing the order of the process. So here you multiply B times C first, and then you multiply in A. And on this side, you multiply A times B, and then you do that result times C. And likewise, the distributive property. So here you have, once again, 3 matrices, and you can add the first 2 together, then multiply A times that result, or you can multiply A times B matrix, and then do separately A times C matrix, and then add those results, and you will get the same thing. So those are things that you could test. All right, we'll look at another example on the next slide. We are back to the example we started before, but now we're going to look at the 2 matrix multiplication parts. The first one we want to multiply is A, matrix A, times matrix B. So matrix A is a 2 by 3 and matrix B is a 2 by 3. So I always look at that inner match first. And there is not an inner match. They must be the same number. So this cannot be completed. And we get to move right on. Okay, so now we want to do B times C. So let's check that. B is a 2 by 3. And C is 3 rows times 1 column, so 3 by 1. And look at that. We have an inner match, and my outer values give me my dimensions. So the result is going to be a 2 by 1, 2 rows, 1 column. I made it kind of wide, though, because I have to do some work in there. All right, so always remember row by column. So it's going to be this row times this column. So we end up with -6 plus 0 plus 10. And then the next row times that same column, because there's only one of them. We have -3 plus 16 minus 6. We can go ahead and simplify that. We end up with a 4. And down here we have a 7. And that is your 2 by 1 result of B times C. In this problem, we're going to give you an example of why you might use matrices to compute revenue, or why we might use matrix multiplication at all. So a clothing store sells men's shirts for $40, silk ties for $20, and wool suits for $400. Last month, the store had sales consisting, they sold 100 shirts, 200 ties, and 50 suits, and they want to know what was the revenue. So you could think about it as two matrices. We have the R matrix, which is the prices or the rates, and this is a row, if you will. So this is your price matrix, and this is a 1 row by 3 columns. So each row or each column represents a different item. And then we have our sold matrix, number sold here, which is a 3 row times 1 column matrix. And this represents the number of shirts, ties, and suits sold. So if I want a new revenue, I need to multiply each item in this row times each item in this column. And they're set up just so the number of shirts times the price of shirts will get multiplied together. So for total revenue, that's going to be rows times columns. And we'll take our first row element, which is 40, times our first column element. So 40 times 100 plus 20, which is the price of ties, times the number sold, and the price of the suits. And they sold 50 suits. So let's multiply this out. We end up with 4,000 for our shirts and 4,000 for our ties. And then we have $20,000 in suits. So when you add that all up, we end up having revenue of $28,000. And that's just a very simple example of why you might do matrix multiplication.